And that concludes the core pipeline and all supporting pipelines. But wait, there's more. For those of you who don't have a background in computer science, I have included a brief explanation on binary numbers, how they relate to bits, bytes, and bitflags, as well as an overview of ASCII. Once you understand ASCII, the Phred score values will make a lot more sense. So, binary numbers. In the decimal number system, which we learned growing up, each position of a number can have one of 10 values: 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. When a position is at its highest possible value, incrementing that position causes that position to reset back to the lowest possible value, and the next position increases by 1. For example, 19 is followed by 20. Increasing the number 19 by 1 causes the 9 in the 1's position to go back down to 0, while the next position, the 10's position, increases from 1 to 2. Now, because there are only 2 possible values at each position for binary numbers, instead of counting like this, they count like this. And for anyone who is just listening to the audio but not watching the video, I just showed 2 series of numbers on the screen. Now that we know how binary numbers work, let us talk about bits, bytes, and bitflags. In the early days of proto-computers, a signal on a chip or wire's electrical circuit could either be high voltage or low voltage. Memory components, either temporary or permanent, would store this information, and thus only have 2 possible states. Such a system naturally lends itself to a binary number system, with the 2 signals being designated as either 1 or 0. The smallest unit of information in computing came to be called a bit, and it is a unit of information with only 2 possible values, 1 or 0. A byte consists of 8 bits, and has 256 possible values. This limit underpins many things in modern computing. It is why some programs cannot parse files with file paths exceeding 255 characters in length. It is why RGB values go from 0 to 255. And it is why the Pac-Man arcade game glitches out after level 255. But going back to the topic of bytes. A byte is usually the smallest unit of information that code will deal with. However, if the information being stored is either yes or no and nothing else, then we only need 1 bit to store that information, not 8. The other 7 bits are redundant. Now, in the early days of computing, data capacity was much lower and more expensive, so there was a strong incentive to utilize every bit in a byte to store information if possible. This still holds true today in very specific scenarios. Ultimately, this led to the creation of bitflags, which are bytes where every bit counts as a separate yes-no piece of information. So how does this all tie back to binary numbers? Well, all bytes can be read as a binary number, and this includes bytes used for bit flagging. For example, a bit flag byte with yes for the first, fourth, and eighth flags, and no for all others would be 100010001. If interpreted as a binary number and then translated back into decimal, this would be 137, which can be broken down into 128 plus 0 plus 0 plus 0 plus 8 plus 0 plus 0 plus 1. 1 byte contains 8 bits, and can therefore contain the data for 8 bit flags. 2 consecutive bytes will, between them, contain 16 bits, with a highest value of 65,536. You may also recognize this number from various places. Now that we understand how bits, bytes, and binary works, we can finally talk about ASCII. In pure data form, all information, such as letters and symbols, are stored as ones and zeros, which can be read as a binary number and converted into a decimal number. Here is an ASCII table, which you can find with a simple Google search. Under the ASCII system, lowercase a is stored as 0, 1, 1, 0, 0, 0, 0, 1, which corresponds to the number 97 as a decimal number. Uppercase Z is stored as 0, 1, 0, 1, 1, 0, 1, 0, which corresponds to the number 90 as a decimal number. The character for 0 is stored as 0, 0, 1, 1, 0, 0, 0, 0, and not 8 zeros in a row. The binary form of the ASCII character for 0 corresponds to the number 48 as a decimal number. And for our last example, the symbol for hash is stored as 0, 0, 1, 0, 0, 0, 1, 1, which corresponds to the number 33 as a decimal number. And now, at last, we can talk about Phred scores in FASTQ files. As stated earlier, FASTQ files use a single ASCII character for each nucleotide to designate the corresponding quality score. Similar to an ASCII table, there are two Phred tables which tell us the corresponding quality score for each ASCII character. Be mindful of the fact that a quality score of 0 does not correspond to the ASCII character for 0. Under the Phred 33 system, a Q score of 0 is represented by the ASCII exclamation mark, which has a decimal value of 33. Under the Phred 64 system, a Q score of 10 is represented by the ASCII uppercase J, which has a decimal value of 74. And so on. Like ASCII tables, Phred tables can be found using a simple Google search. And that concludes the presentation, appendices and all. Slides and supporting documents can be downloaded from the links in the description below. My name is Angelo Chan, and I hope you enjoyed this video series.